to the next piece here, which is the main attraction. Looking forward to welcoming Dr. Jennifer Francis, and she is a senior scientist at the Woods Hole Climate Research Center, which was formerly the Woods Hole Research Center down in Falmouth. Previously, she spent 24 years as a research professor in the Department of Marine and Coastal Sciences at Rutgers University, where she studied the Arctic and climate system and how rapid Arctic change is affecting areas beyond the Arctic, particularly extreme weather in the Northern Hemisphere. She has testified to the U.S. House of Representatives Science Committee in 2019 and to the Senate Committee on the Environment and Public Works in 2013. She has taught courses in satellite remote sensing and climate change issues, and has also co-founded and co-directed the Rutgers Climate and Environmental Change Initiative. Jennifer earned a BS in meteorology from San Jose State University in 1998 and her PhD in atmospheric sciences from the University of Washington in 1994. She and her husband have circumnavigated the globe by sailboat during the early 1980s, including the Arctic, which is where her interest in the region began. Please join me in Zoom welcoming Dr. Jennifer Francis to discuss how the Arctic meltdown affects tropical storms. And I'm going to stop sharing, Dr. Francis. Go ahead, take over. Can everyone see that?
Is that working okay?
Yep, go to slide version. Yep, there you go. All right.
Okay, good. All right. Well, I want to thank Barbara and Jeff for inviting me back. I enjoyed myself last year, and I was very honored to be invited to come back and talk to you guys again this year. I wanted to mention again that just as of this week, the Woods Hole Research Center in Falmouth, where I work, is now the Woodwell Climate Research Center. So our new name reflects better who we are, what we do, and also is a tribute to our founder over 35 years ago, George Woodwell. So we're very excited about this change. It was just launched literally this week. So hopefully some of you got some of that information in the mail. So this is a great topic to be discussing today. It's very timely. Obviously, we're in the middle of hurricane season. We're also looking at a summer where we're going to be perhaps breaking a new record in the amount of sea ice floating on the Arctic Ocean. And this is a very big deal. What I want to talk about today is how these two seemingly very disparate things, tropical storms and the melting of the Arctic way up in the far north, could possibly be connected. So I want to start by looking back to the last time this neck of the woods had a real hurricane, and that was Hurricane Bob, almost exactly to the day 29 years ago. And it was a very damaging storm. It wasn't anywhere near the storms that we had in 1954 and 1938, but it was a doozy. And here we are this year looking at what all of the reliable organizations that predict the activity of a hurricane season have decided is going to be an extremely active summer. We're already seeing that. We're already looking at the letters in the names of hurricanes is already up to K actually, and all of those since C have been the earliest that the storm with that letter has occurred. So we're already looking at a record-breaking hurricane season here. But it has been 29 years since we've had a big storm, so I thought it'd be worth looking back and just remembering a little bit what a big hurricane looks like around here. There's some great pictures that were put together by the Boston Globe in a nice summary back in 2016. So here's what Woods Hole Harbor looked like. We're not talking about a little storm here. A real hurricane can do some amazing damage. Bob was actually the worst, had the biggest impact between Buzzards Bay and Narragansett Bay. So it didn't affect the outer Cape very much, but certainly the south coast of Massachusetts and Rhode Island were hit hard. But you know, Falmouth didn't escape. There's a big boat sitting on somebody's lawn there. But here we are today, almost 30 years later, and the climate that hurricanes are forming in now is very different. Obviously, the globe has warmed a whole lot. This is showing the temperature differences from normal for last year, averaged over all of 2019, and how they differ from what we consider to be normal. And what you see is all these colors. There's no numbers that are negative. Everywhere is warmer than it used to be by quite a lot, especially that far northern area, the Arctic. And of course, connected with the warming up there, as I talked about last year with you all, is the fact that we've lost a tremendous amount of the ice that floats up on the Arctic Ocean. So hopefully you can see my arrow here so I can point some things out. Up in the upper right here is looking down on the Arctic Ocean and what it looked like in a typical summer back in the late 1970s. And here's what it looked like in 2012 when we set our the most recent record low amount of sea ice. And so what you can see is the white area now is so much smaller than it used to be. And this red and orange and yellow colors here are where there used to be ice normally. So between what it used to be like and this 2012 record, literally we've lost half of the cover of sea ice on the Arctic Ocean in only about a 40-year time span. And that is incredibly fast and a huge change to the climate system. And then if you take into account how the thickness of the ice has changed and you multiply that change in thickness by the change in area, you get the change in the volume. And we're looking at a decline of 75%. So 3/4 of the ice in the Arctic is now gone. This is just a huge change. And by losing all this ice, of course, ice is very white and reflective. It reflects a lot of the sun's energy that hits it. The Arctic is literally darker now, which makes the Earth darker now. So much more of the sun's energy is now being absorbed into the climate system rather than being reflected back to outer space. And this has some very interesting and disturbing effects. I call the sea ice loss a threat multiplier, because by losing this mirror of the Earth, it's actually causing global warming to be larger than it would be otherwise by 25 to 40%, something in that range. So the global warming is much worse because of losing all this ice up in the Arctic. And that extra warming that's happening in the Arctic is causing the glaciers up in actually all around the world, and also the ice sheets in both Greenland and Antarctica to accelerate in their melting, which in turn is leading to an acceleration of sea level rise. So as we look back over the hottest 10 years on record, what we see is if you look at the dates there along the bottom, they're all very recent years. And in fact, the last 5 years were the hottest 5 years. And 2020, the year that we're in right now, is almost certainly going to end up in the top 3. So we are not on a good trajectory here. So there's more heat in the atmosphere now because of the greenhouse gases we've been dumping into the atmosphere for the last several decades. We're trapping more heat. There's more heat in the atmosphere. There's also more heat in the oceans. The oceans actually take up about 90% of the heat that's trapped by greenhouse gases like carbon dioxide and methane and water vapor and some other ones as well. And if we look at, this is just from a couple days ago, if we look at the Atlantic Ocean temperature departures from normal, so this is comparing the temperatures today or 2 days ago from what they normally would be. These red colors are off of our coast here are telling us that the ocean is a couple degrees Celsius warmer than it should be. And it's been like this for several years now. We see that it's warmer than normal all through the Caribbean, into the Gulf of Mexico, and especially as you get up to the far north. And if we look at how much heat over time has been absorbed into the ocean, going back to the late 1950s here, what we see is there's a very dramatic increase in the heat content of the ocean. This is also super important when it comes to hurricanes, and I'll tell you why in a second. The other thing that we're really concerned about is how the moisture in the atmosphere is changing. So hopefully you can see this animation. This was taken just today. It's showing the amount of water vapor in the atmosphere all around the globe. And it's really kind of hypnotic and fun thing to look at. So all these orange colors and even some pink colors here are showing you where there's a lot of water, a lot of moisture in the atmosphere. And this is water vapor. It doesn't include clouds. It doesn't include rain. It's just the gaseous form of water that's in the atmosphere. And there's some pretty cool things that you can point out here. So here's one of the tropical depressions that's forming right now in the middle of the Atlantic Ocean that's heading towards the Caribbean islands. There's another one forming just west of the Caribbean islands heading towards Central America. And we even have a couple more out here that are starting to brew over Africa. There's a very strong hurricane about to hit Cabo San Lucas area, and you can see there's a lot of moisture just all throughout the tropics, which is typical for the tropics, especially during the summer. But there's also some cool things I just want to point out. You can see these swirls that extend way far north, and these are part of storms, normal storms that you'd find at high latitudes. So one of the jobs of storms is to take all this extra tropical moisture and distribute it to the higher latitudes. And it's really clear to see in an animation like this. It's just kind of a cool thing. So regarding this moisture, what we're seeing since the late 1970s is a very distinct increase in the amount of moisture that's in the atmosphere. And I think I mentioned this last year when I talked to you all, but in terms of hurricanes, this is a huge deal, because if we have more heat in the atmosphere and more heat in the oceans and more moisture in the atmosphere, these three things are the fuel for storms. Not just hurricanes actually, but for all storms. So the fact that we're seeing all of these things increase dramatically, all connected to human-caused climate change, is affecting hurricanes in a big way. Particularly, we're seeing hurricanes that are of the strongest categories, so category 3, 4, 5. We've seen an increase in the frequency of the strongest storms. We've seen an increase in the intensification rate of storms, so how fast a developing tropical storm will, say, develop into a Cat 2 or a Cat 4, something like that. And we're also seeing the distribution of storms around the Atlantic change. So as the oceans get warmer, those storms are able to travel farther north before they lose their tropical characteristics. So another impact that I mentioned before of the melting and warming Arctic is the fact that it's causing the seas to rise even faster, an acceleration of sea level rise. Now, the reason that sea levels are rising can be broken down into these components. The biggest one is the melting of glaciers. So this is the glaciers and the ice that's sitting on top of land. So when that ice melts, it goes into the ocean and it adds mass to the ocean. The second biggest component is what's called the thermal expansion. So as the oceans get warmer, the water actually grows, it gets bigger. And so as we warm the oceans, as I showed you, that's been happening very steadily over time. The oceans are actually getting bigger. And then we have these melting of the ice sheets, the melting of Antarctica and the melting of Greenland. Both of those are accelerating really fast. And if we look at how these components are changing over time, going back to the early 1990s, we see these various components and how they add up to the total amount of global sea level rise. So here's that thermal expansion, the growing of the oceans because of them getting warmer. You can see how that's increasing, especially lately. And this blue line here is the contribution from the melting of ice mostly, so the glaciers and the ice sheets. And when you add those two together, you get the total change in sea level. And you can see there's a general upward curve in this line. So we are seeing now an acceleration of the pace of sea level rise. And of course, just want to mention also that sea level rise you'd think might be the same everywhere, but it's not. It's happening faster in some places than in other places. And this map is showing you where those places are, what places where sea level rise is happening the fastest, which is where it's red. Notice that off of our coast is one of the places where sea level rise is happening the fastest. Also off of the east coast of Asia, we tend to see this off the east coast of continents. So there are places where it's definitely happening faster. Unfortunately, one of those places is where we live, and here we are right there. So the reason sea level rise figures into this story is, of course, because as the seas get higher and as a hurricane comes ashore, that storm surge generated by the hurricane is riding on a higher sea, and so the storm surges are also going to be higher. The waves from the storm are also riding on a higher ocean, so those waves are going to reach farther inland and do more damage. So the final thing I want to mention that connects Arctic warming to hurricanes is a much less direct connection, and this is where some of my research comes in, is how the rapidly warming Arctic is affecting the upper level winds in the atmosphere. And those are the winds that actually steer the paths of tropical storms. So there are basically three things that are going on here related to Arctic warming. As the Arctic warms much faster than areas farther south, and I talked about this last year, this has the effect of weakening the flow of those upper level winds. So those steering currents are actually getting weaker. We're also seeing the jet stream, which is the river of air high over our heads that creates and steers not just hurricanes, but all sorts of storms. Those waves are getting large more often in the jet stream. And when those waves get really big, they tend to move much more slowly. And so we get this stagnation of weather regimes. And what that can do, we'll talk about how some examples of storms that these factors have come into play. But just to give you a sense for what I'm talking about here, here's an example of a jet stream pattern. So these are the winds in the upper levels of the atmosphere. These greens and yellows here are where the winds are really strong. That's where the jet stream is. And this is an example of when the jet stream is in a very wavy state. And when you get these big waves like this, they tend to get stuck in place for a long time. This happens to be a case when Hurricane Irma came along, and the storm came along through the Caribbean, up through Florida, and these relatively weak winds down here made Irma travel very slowly, and it ended up dumping a lot of rain on Florida. So I actually have a graphic of that and some examples of some of what I call the unruly tropical storms that we've seen lately. So the first one is, in fact, Irma. And this was notable because it was tied for the strongest Atlantic hurricane ever to make landfall. It was a very strong storm. It ravaged many of the Caribbean islands and Puerto Rico, and then it came ashore in Florida and dumped over 20 inches of rain in parts of Florida. Another one you'll remember was Hurricane Harvey just 3 years ago now. And it was notable because it came along up into the Gulf of Mexico. And in this case, the steering winds were basically zero. It came in from the Gulf of Mexico, came in towards Houston, and it just stopped for 2 or 3 days in one place. The result was the area all around Houston saw rainfall exceeding, if you can still see those numbers, over 20 inches, in some places over 40 inches of rain. And if you've ever been to Houston, you know it's really flat. So that rain had nowhere to go. It was some extreme flooding, and some of the residents, like this fellow here, were not happy about it. Hurricane Florence was another example the following year that came into the Carolinas, The steering winds were very weak. It came ashore and dumped almost 20 inches of rain on much of the coastal region of North Carolina and Virginia. You'll remember Hurricane Dorian as well, that came into the Bahamas. And again, you can see in this animation, it just stayed in one place. And it was a Cat 5 when it came into the Bahamas, and it just completely destroyed the Abacos. And again, the steering currents for this storm were zip. And we think there has been some research to show that these slow moving and stalling storms are happening more often and are expected to happen even more often as we go forward. And then just a couple weeks ago, we had Isaias came up the East Coast. Looked like it was going to be a problem for us out here on Cape Cod, but most of the damage that it caused was mainly due to heavy rainfall around the DC, Baltimore, Maryland area. So here we are in the middle of hurricane season. And as I mentioned, all the predictions agree that it's going to be a very busy year. And as we look across the tropical Atlantic right now, this is today, what we see are the storm that I mentioned in the Caribbean already that's just getting its act together. It doesn't have a name yet. There's another one right behind that, just coming in towards the Caribbean islands. It also doesn't have a name yet. And then there are two more just starting to form over Africa. So we could see this week be a very active week. We could add 4 more names to the list that's already long for this time of year. As I mentioned, our ocean temperatures, especially in the Gulf of Mexico and along the East Coast, are way above normal. So if a storm does come up this way, it's going to have plenty of energy to feed off of. We also have no El Nino happening this year. El Nino, as you might know, is a temperature pattern out in the Pacific Ocean, which you'd say, well, who cares what's going out there? I mean, what does that have to do with the Atlantic? But it turns out when there's an El Nino, which means that there's warm water off the west coast of South America, it tends to create a lot of shear in the atmosphere in the Atlantic. So shear means that the winds are blowing from different directions or at different speeds at different levels in the atmosphere. And it makes it very hard for a hurricane to get its systems going and to get its engine going. And so the fact that we don't have an El Nino means that we don't have very much shear. And so it's conducive to hurricane formation. And it's one of the reasons why a very active year is being predicted. We also have, as I mentioned, we're flirting with a new record low amount of sea ice up in the Arctic this year. This was taken just, this is the sea surface temperatures from just last week. And so here we are at Cape Cod, here's Greenland. And all of these red and orange yellow colors here are telling you the ocean is very warm up in the Arctic. And so we'd expect to see some pretty weak and perhaps squirrely steering winds when a storm does come up our way. So interesting times, interesting conditions. And I think I might have mentioned this last year, but if you want more information, I've got a couple of articles that came out in Scientific American over the last couple of years, one in April 2018, one last year, and they have more information in there if you're interested. And with that, I'd love to have some questions.
Right, Jennifer, if you'd unshare your screen there for a second. All right, if anyone has any questions they would like to ask Dr. Francis, please go ahead and ask them in the chat session that you'll find at the bottom on the bar, the toolbar. All right, let me get to, oops, sorry, here I'm trying to navigate around. Where did it go? All right. Well, I'm gonna ask one. I'll start.
Go for it.
So this is the fellow remote sensing scientist. I spend a little time doing that as well. So I guess my question is, um, we're having a fairly large explosion of satellite coverage lately. I'm thinking cube satellites and microsatellites, and the skies are getting pretty full up there. And then which provides the opportunity for a fairly dense sampling network. Combine that with advances in computing, whether that be AI or quantum computing in the future or cloud computing now. What role do you see all that technology playing in increasing the modeling accuracy that we have when it comes to climate modeling, as we move forward? Do you see, big advances moving forward because of technology, or it seems we're on a sort of a slow creep forward and we get a little bit more accurate every year? What's your take on that?
Yeah, so that's a great question. We do have an incredible amount of satellite information coming in now. We have new sensors, we have new platforms. And as you mentioned, one of the main ways that satellite information helps us is to feed into the forecast models that are used to try to predict whether hurricanes are forming, how much moisture is in the atmosphere, what the winds are doing, all of that, especially out over the oceans where we don't have any people to send up weather balloons or to take measurements in sort of the more normal way. So the satellites play a huge role in filling in those big gaps over the ocean. It's a real challenge to take some of that information and feed it into those models in a useful way. Oftentimes that information doesn't come at the right time. It might not be at the right place. It might not be at the right level. So there's a whole science of what's called data assimilation that looks at how do you take this information that satellites give us and use it in a helpful way in models. And actually satellites can only see wavelengths of light. So they measure light at all the way from the radio spectrum all the way through to the ultraviolet. And those different wavelengths give us different kinds of information about the atmosphere and the surface. And so translating all those things and making it useful is a real challenge. But I have to say, one of the things that we're really lacking in terms of our ability to forecast hurricanes right now, we're doing a pretty good job with the tracks. Where we're not doing a good job still is intensity forecasting. And the reason for that is because we don't have a way to measure how much energy is contained in the ocean. We can measure the surface temperature well, but we don't know how deep the layer of the ocean is that is, say, warmer than normal or maybe not warmer than normal. And so that is really where the battery for the storm is. And not knowing how thick that layer of energy is really the challenge that we're facing right now. Can't do that from satellites.
All right, another question here from Sarah Griscom. I'm curious to know your thoughts about the intense warming of the Gulf of Maine. Why might it be warming more than other areas of the world? I know you showed that little red spot off of the New England coast there. What's driving that?
That is another great question. So it turns out that is tied up with changes in the really global scale ocean current patterns that are changing. And if I could share my screen for just 1 second.
Yep.
Let me see if I can show you something that's pretty cool, actually, and that it relates to that question. Okay, can you see that?
We see you.
You see me.
There you go.
Okay. So this is a new paper. It just came out like a week or so ago. And it's showing the trends in the surface temperatures of mostly the Atlantic Ocean. And so what you see is this really strong warming trend off of the northeast coast of North America here. And downstream of that, you see this huge area south of Iceland and Greenland that's been getting colder than normal. So both of these things are related to the same process that's going on. And basically what's happening is this large scale current system that brings warm water from the Gulf Stream up along the East Coast and across the ocean to the UK is slowing down. And so what's happening is we think that it's mainly this cooling area that's doing the slowing. And that cooling area there is actually an area of fresher ocean water sitting on top. And it's because of that melt water coming off of Greenland, that extra melting I talked about, as well as extra river runoff that's going into the Arctic Ocean and then flowing down into the North Atlantic. So that fresh water sitting on top of the ocean there is preventing the ocean from mixing as well as it normally would from the surface down to deeper levels. And so that lack of mixing is keeping one of the forces that drives the ocean circulation from happening as well as it normally would. So normally you'd cool this ocean here, you'd freeze some ice, it would create really dense water that would sink really rapidly, and that's one of the things that drives this whole ocean circulation. But that's being slowed down because of this extra fresh water coming out of the Arctic, and that's like backing up, sort of like backing up a sewer pipe. It's keeping all that warm water from flowing out across the Atlantic as it would normally do. And so that's one of the main reasons we're seeing this pileup of warm water along our coast. Long answer, but kind of an amazing thing that's going on. Okay, let me unshare again.
Another question here from Michael Westgate. Could you comment on the two hurricane forecasting systems, the European and the American models?
Yes, and that ties in with two questions ago. So generally speaking, the European model gets higher marks for its ability to forecast the tracks of hurricanes. The reason is because they do a better job of assimilating all of that satellite data that we were talking about. They have a much more sophisticated system of doing that. They've dumped a lot of resources into improving the way they take all these different kinds of information from satellites and from other places and getting it into the model and improving the skill. So it's not so much that they're forecasting the hurricane itself better, they're forecasting the global circulation better in which those hurricanes are embedded. So if you get the large scale wind patterns right, you're going to get the tracks of the hurricanes better too.
Gotcha. Thank you. All right. Let's see. I think we answered Dee Dee's question with your last slide, which was what's temperature of melting ice has on ocean temperature. It seems it should have a cooling effect, and you covered that. From Michael Riley, if the U.S. if the jet stream generally flows west to east across the country, what is pushing or pulling the tropical storms eastward, or I guess westward over the Atlantic towards the U.S.?
Right. So the jet stream is generally quite a ways north of the area where hurricanes form. Hurricanes form in what's called the main development region normally, which is the tropics. And that area of the ocean is where the trade winds are. The trade winds blow from east to west. And so these tropical waves that form are basically embedded in this westward flowing wind regime. And they don't start to turn north and then finally eastward until they get up into the latitudes where the jet stream can then affect them.
Gotcha. Okay, and I think we have one last one here. Do you have any hope, from Frank Messina, do you have any hope at all that we can reverse the increases we're having in global warming?
I have absolutely no hope that we can reverse it, but I have lots of hope that we can slow it down. and we have to slow it down. We have to do everything we can do to slow down our emissions of greenhouse gases so that it won't be so bad. We can't turn it around because we've already put, especially so much carbon dioxide in the atmosphere. And carbon dioxide lasts 100 years. One molecule on average lasts 100 years. Once you put it up there, it's going to have an impact for a long time. And so we've already baked in a lot more warming into the system. And once you start a bunch of these processes happening, like the melting of the ice in the Arctic, what happens is you melt some of that ice, you reduce that mirror that I was talking about, you absorb more of that sun's energy into the ocean up there, it warms the ocean, it melts more ice. This is a vicious cycle, or a positive feedback, we call it. And once you get some of those in motion, they're very hard to turn around. So yes, we need to do everything we can to slow down our emissions of greenhouse gases and other changes like burning the Amazon rainforest and using so much nitrogen-based fertilizers. These are all contributing to the warming of the planet. These things we have to do because we're going to leave a planet for our kids and their kids that's really going to be unlivable in a lot of regions where there are a lot of people living now. And so we have to do everything we can do. We can't turn it around, but we can definitely slow it down.
Anything we do to mitigate it buys us some time to build resiliency. So,
and maybe also come up with some technology to actually extract carbon dioxide and methane and other heat trapping gases from the atmosphere.
Yep.
Thank you.
Okay, well, I think that's it on the questions. I want to thank you very much for presenting to us again this year. It was, as usual, very able to absorb with great graphics and timely data that, literally is days old. So I appreciate that, and thank you for your time. And we look forward to, if you wouldn't mind putting this on our website, if that'd be okay. So we can educate some more people. So.
Yep. Sorry to be so depressing again. I know I depressed everybody last year, but
No,
what can I say?
It is what it is. So
it is what it is.
It is what it is. All right. So, all right. Thank you, Dr. Francis. Appreciate